Students, welcome to my 8th class in nuclear physics. In our last class, we had completed our first unit and now we move on to the second unit. So the second unit is 10 marks worth and it consists of nuclear models. And we have these three topics in this second unit. Qualitative introduction to nature of nuclear force, qualitative discussion of the liquid drop model in relation to the semi-empirical mass formula, and qualitative discussion on the shell model of the nucleus. These students, the first topic here is qualitative introduction to nature of nuclear forces, and we have actually already touched this topic in the first unit. Since they have said only, they have mentioned qualitative discussion, that means we have not much to do with a mathematical theory about it. So qualitative discussion on nature of nuclear force, because you see, first of all, we already saw that what was nuclear force. So nature, it is the strongest force in nature. Number two, it is short range attractive. And I'll add one more point here, and very short range. Very short range repulsive. It is charge independent. Some also add another point to this charge: symmetry. And I wouldn't like to name this as two different points. Actually, to me they are the same, but then you should know what is charge independence and what is charge symmetry. Number 4 is saturation. Number 5 is spin dependence. And the number 6 is exchange type. So I would like to once more elucidate point by point. Strongest force in nature, I don't think there's much to explain here, because we have got the gravitational force, electrostatic force, and electromagnetic force, and other forces. All forces in nature, among all those forces, the nuclear force is the strongest. Now when I say nature of nuclear force, what we mean is the force between the protons and the neutrons inside the nucleus. That is the only force that we talk of when we say nuclear force. So the force between these particles are the strongest force in nature. They are attractive. Yes, short range attractive. What is the meaning of short range attractive? That can be explained by comparing it with the electrostatic force, because in electrostatic force you know that what happens is that when you have a charge, the effect of the charge is felt somewhere close to it, far off, up to quite a distance, because F is proportional to 1 by r square. So as the distance falls, as the distance becomes bigger and bigger, not falls, distance rises, the force falls like this. But then no such thing happens in case of nuclear force. In case of nuclear force, it is the force near a proton or a neutron is felt only within the nucleus, and the nucleus is a very small area. As we know, it is 10 to the power minus 15 centimeters 1 Fermi, this much. So it's very strong inside a certain area, and then it suddenly falls like this. So we have already seen the diagram and all this. We have seen that if this r is the distance from the center of a nucleus and it goes this way, then up to this point where r is equal to capital R, where capital R is the radius of the nucleus, till here the force is very strong. So very strong, and then what happens beyond this, when r is equal to r, it becomes 0. So that is very strange, because gravitational, electromagnetic and all these forces that are known to us are not of this type. So that is very short. And what happens when look at this second point, short range repulsive. Short range repulsive means if I proceed to bring suppose these are two protons, or one proton or neutron, or both neutrons. So in case, let me draw it slightly big like this. This is a proton and this is another proton. So the distance between them is definitely equal to twice r. Let me call this rp if they are protons. Rp is the radius of a proton. In that case, what happens is that if we try to force the neutrons or the protons, these two particles, closer this way, if we press it, imagine that we are pressing it, so in that case what happens, the force becomes repulsive. That means if we try to decrease this distance beyond this, less than twice rp, then what happens, the phase force becomes repulsive. And that is the reason why protons and neutrons, they maintain their shape actually, otherwise they would be squeezed together. So that is the explanation of the short range repulsive. Now coming to charge independent, that means whether it's a proton and a proton, or a proton and a neutron, the force of attraction is the same, the magnitude of the attraction is the same, and that is meant by charge independent. It means whether you have a charged particle, proton attracts another proton with the same force as the proton attracts a neutron. That is charge independent. Now what about charge symmetry? Charge symmetry is the force between a proton and a proton, and a neutron is the same. That is charge symmetry. That means what? Proton, proton, neutron, proton, neutron, neutron, all are same. So some divide this point into 2 points, which I would not agree that much, because charge independence should be able to explain all these things. Now coming to saturation. When I talk about saturation, which we had mentioned earlier also, what is saturation? Saturation is that when I have a proton inside the nucleus, then it will be affected, or it will affect only the nearby particles, whether it be proton or neutron, and after that it will not affect the ones which are at a distance. That means as if the force, nuclear force due to this proton gets saturated by attracting the nearby, and its effect cannot be felt on the particles lying at a distance, that only its nearest neighbors, that is the exact actually term used, that a nucleon, that means whether it be a proton or a neutron, it attracts only nearby nucleons. So the study material for this will be shared to you. And then spin dependence. Now what is this spin dependence, which also I had touched upon in my previous discussions. So spin dependence comes from the existence of a spin of the nucleons. We have learned in our first unit that neutrons and protons have got a spin which is connected to the spinning motion. So now proton, but then spin is a vector quantity because spin is related to the rotation of a proton about its own axis. So it's just like in atomic physics you had learned about the electron spin. So a particle spinning like this and a particle spinning this way, this is the anti-clockwise, this is the clockwise direction, definitely the direction of the spin vector will be different like this. So in that case we have two cases like the spin up and the spin down. So if one is like this, the other will be this way. So in case of the nucleus, suppose I have got a proton and a neutron and a proton. So this is my proton and this is my neutron. So in this there may be two cases. First, their spins may be parallel or their spins may be anti-parallel. So in this case the total spin of the whole nucleus will be different, and so the forces will also be different, which we'll learn later on. So this is spin dependence. So this depends, that means the force not only depends upon the particle, it also depends on the spin, because spin is just a quantum number, and quantum numbers determine the state of particles. That's why that is spin dependence of nuclear forces. And now coming to exchange type, this was first proposed by the meson theory of Yukawa, which I had probably mentioned, Yukawa's meson theory. According to Yukawa's meson theory, let me clean my board. Suppose I have a proton. Now a proton, it is, according to his meson theory, we know that a proton is a positively charged particle, and a proton emits a negative pion. Pions are a set of particles, they are family of particles, pions. They are pi plus, pi minus and pi neutral. So what happens is that these are three different types of pion, and in an interaction for a p and n pair, nuclear force between a proton and a neutron is maintained in this manner. By exchanging a particle continuously with each other, the proton and the neutron maintains this attraction. That was what Yukawa has proposed. What does it mean? It means that proton sends a negative pion and this becomes a neutron. And what about a neutron? The neutron is like this, and this is the proton. So by continuously changing the pion, they maintain this attraction. It is like a ball thrown between two persons like this. This is one person, he throws this, okay, he is wearing a cap like this, he throws this cap to this becomes like this, and now this is not there. Again this throws it like this. So this is what is happening. They exchange the caps, which I mean the pions, like this, and this is type of force is called exchange force. That is the exchange nature of force, and we'll talk more about exchange force in our later classes. Now exchange force, the idea of exchange force comes from the idea of action at a distance. Now when I say action at a distance, we know that when I apply a force on a particle or on a body, it starts moving. But that is what happens in mechanical movements. But what about electrical? You see, I have a charge here. When I bring another charge here, even though there is no bodily contact between the charges, it will experience a force. And similarly in case of gravitation, you know that even though on the surface of the earth a body, there is no physical touch there is like this. So nuclear force is also that type of force